So the first part of this thermo unit was about calculating energy changes, and the second part gets us into spontaneity. However, on the AP test, they don't use that term spontaneous anymore. We refer to it as thermodynamic favorability, which really does look at all the factors that affect whether or not a reaction is likely to occur. One of those factors is something called entropy. Now, previously we had enthalpy. Enthalpy is just a fancy word for heat energy. So when they say calculate the enthalpy change, it just refers to the change in heat energy. Entropy is a little different. Its symbol is S, which is random, right? So we'll see like delta S. That's the change in entropy. It's a measure of disorder, molecular disorder. Now, your life could also have entropy. It's a measure of disorder. And we say that nature favors an increase in entropy or an increase in disorder. So, for example, let's say you clean your room and everything is really organized. Well, does it have a tendency to stay that way over time? Probably not, right? And our life just favors disorder, that we have all the best intentions of keeping our closets organized, and you throw a couple socks in the corner and all of a sudden it's a giant pile of laundry. That our lives just favor disorder. Nature favors disorder. On a chemical level, we favor reactions that have an increase in disorder. And so particles that have disorder are obviously things like gases have high entropy. Gas particles are very disordered. They're bouncing all over the place. Well, that might be in contrast to like an ionic crystal. Ionic crystals are very low entropy. They're very orderly, where you've got this repeating pattern of oppositely charged ions in a very organized crystal structure. Something like an ionic crystal would have very low entropy. The more moles I have, the more disordered they could be. Like if I have less particles, there's a better chance that I can keep them orderly. But as you add more and more substances to the mix, more moles tends to create more disorder. So, I could take like 2 kindergartners on a field trip, and I feel like I could keep them pretty orderly. You ask me to take 50 kindergartners on a field trip, and it's mass chaos. I can't keep them all in a straight line. And so we say more particles, more entropy. We also think about pressure, especially when I'm looking at gases. At a lower pressure, we say that particles usually have higher entropy, because low pressure means larger volume. And so again, if I've got these gas particles in a larger space, that means more space for them to spread out and be disordered. At a higher pressure, which would mean a smaller volume, then again, there's more chance that the particles are closer to each other and more orderly. So again, if I had 50 kindergartners, but I can just keep them in one small room, then I'm not going to lose them. I can keep them more orderly. But if I've got 50 kindergartners in a giant zoo, then they're all over the place. And so I can't keep track of them in a larger space. Nature favors an increase in entropy. So we say thermodynamically favorable processes will have an increase in disorder. Now, here's some good examples. Which of the following has greater entropy? So greater entropy, solid carbon dioxide, like dry ice, or gaseous CO2? So that's an easy one, right? The gas particles are more disorderly. In the solid phase, at least they're all kind of packed real tight together. What about nitrogen at 1 atmosphere versus 1 times 10 to the negative 7th atmospheres. So when I think about pressure, those gas laws come back. Higher pressure, a higher pressure, if I'm thinking like I'm pushing down on gas particles in a syringe. High pressure means a smaller volume. Well, in a smaller volume, I can keep those particles more orderly. It's in a higher pressure. That would mean a smaller volume. But if I have a smaller pressure, that means a larger volume. Larger volume, the particles can be all over the place, highly disordered. Here they're looking again at predicting the sign of the entropy change. Positive delta S, we're going to say, means an increase in entropy or an increase in disorder. Negative delta S means that the particles are becoming more orderly, more organized. So what if I have solid sugar and I add it to water to form a solution? So in the solid phase, the sugar molecules are all kind of packed real tight together. But in solution, they're going to dissociate from the original solid. So they're all kind of swimming around randomly in the solution. In solution, those molecules are more disordered. So we're going to say positive delta S, that there's an increase in disorder. And that would be for anything in solution. As those particles dissociate and start moving around in the water, they're more disordered than they were in the original solid. What if I have iodine vapors, which vapor means they're gas and bouncing all over the place, that condense on a cold surface to form crystals? Iodine vapors can deposit as solids, like solid crystals. Well, in the solid phase, the particles are all packed real tight together. This is a decrease in disorder. We say negative delta S. Or we could look at it from a chemical reaction. And so a couple things I look for. In C, I've got solid calcium carbonate forming solid calcium oxide and carbon dioxide gas. Well, number one, I'm starting with solid and I'm forming solid and gas. So by forming gas, those particles are going to be more disorderly, bouncing all over the place. That might be one sign that this is going to have an increase in disorder. Or I could look at this and say, well, I'm starting with 1 mole of reactant and I'm forming 2 moles of product. And one of the products is a gas. So there's definitely an increase in disorder or an increase in entropy. In part D, I've got 2 moles of SO2, 1 mole of oxygen, forming 2 moles of SO3. Everything's gas. So I usually do kind of look at the phases. Am I going from like solids, which are low entropy, to liquids and gases, which are higher disorder? Well, here they're all the same. They're all gases. But I am going from 3 total moles down to 2 moles. So less gas would mean less disorder, a negative delta S.